mathematics that goes far beyond solving equation. But why is it important? Abstract algebra helps us understand the deep structures that underpin mathematics. It provides the language and tools to study symmetry, transformation, and system of logic, with application ranging from cryptography and computer science to physics and chemistry. By understanding how abstract systems operate under certain rules, we can design algorithms and models that are efficient, secure, and reliable. Key topics in abstract algebra include binary operation, which define how elements within a set interact. Group, which are set with an operation satisfying closure, associativity, and inverse, often used to model symmetry permutation, which represent rearrange of elements and are crucial in cryptographic system, and combinatorics of isomorphism, which are structure-preserving mappings that show when two algebraic systems are essentially the same, and cosets, which are used to partition groups and play a significant role in solving equation and understanding group structure. These concepts together form a powerful toolkit for addressing a real-world problems through mathematical abstraction. By the end of this video, you'll see these abstract concepts are not just theoretical, they are tools that help us model and solve mathematical real-world problems.
Nice. What I have here in my hand is a Rubik's Cube, which is actually a group. And I can prove it to you by confirming the 4 prerequisites under the operation asterisk, which is basically the move that you can do on a cube, like so. Now, it's closed because no matter what move I do here, right, it would still be in the group of moves that I can do, right? And it's also associative because the grouping of the moves doesn't matter as long as the sequence stays the same, which is also what makes it a non-abelian group since it isn't commutative. It also has an identity element because basically you can just not touch anything here and not move anything, right? And everything also has an inverse because, for example, if I do this sequence of moves, right, all I need to do to bring it back that nothing happened is basically do the reverse of what I did. Like so. Right? Now, knowing this group actually helps cube solvers create better and faster algorithms to solve a cube using concepts in group theory like commutators and conjugates and a bunch of other stuff, right? Like creating an algorithm here, right? Where if it's like this, you can just do these sequence of moves and it gets solved, right?
Wow naman! Wow!
Another notable example is the 4 possible orientations of a mattress and bed frame, which creates a mathematical structure called the Klein group. We use a cell phone and a selfie stick as a representation for these positions. The first position is rest or no movement, which is the identity. Secondly, a rotation that flips the phone from front to back. Third, pitch, which is a flip from top to bottom. Lastly, a yaw, which is a rotation around the vertical axis. Furthermore, each operation is its own inverse, meaning performing the same motion twice will result in its original orientation. Hence, the group's multiplication table demonstrates how combining any 2 operations lead to another operation in the set. For instance, a roll followed by a pitch equals a yaw. Moreover, the group is commutative, meaning the order of these flips does not matter. Therefore, the cell phone orientations under these flips corresponds to the Klein group.
To sum up, abstract algebra offers a basic framework for understanding complex mathematical structures and the range of application it has in various fields. Using concepts like groups and binary operations, we can explore systems that provide structured examples of symmetry and operations. With the Rubik's Cube and the mattress examples showing how abstract algebra may be used to analyze seemingly straightforward objects and behaviors, it provides deeper insights into their characteristics and relationships. These examples not only demonstrate abstract algebra's versatility, but also its significance in addressing real-world problems and expanding our mathematical knowledge.